Okay, stats. This is the second half of the notes for section 2-1. So you'll need this note sheet out, and we are on the second page, starting with relative frequency distributions. So get this note sheet out, and we will go through the second half of this notes, and then I'll give you time to work on your homework assignment. Hopefully you started that yesterday and could kind of see how much of a pain in the butt that is, so you can spend some time doing that today. So there's in addition to a frequency table or frequency distribution, which looks like this, it's kind of a mess from yesterday. Our frequency distribution that we put together looks like this. In addition to that, or just to a regular frequency, we have something called a relative frequency. Okay, so relative frequency means in relation, I'm going to say relating to the total. Okay, so relating to the total or relative to the total, how much is in each class. Okay, so here's how this works, and we write it as a proportion or a percentage. We're going to write it as both when I fill out this table. So this was the table that we did yesterday, and we said that, here are my classes, and then there's 11 numbers that are in this first class, 24 numbers that's in that second class, etc., right? Okay, when we do relative frequency distribution, okay, first of all, we need to identify how many numbers we did total. Okay, so 11 plus 24, that's 35, plus 10 is 45, plus 3 is 48, and plus 2 is a total of 50. So we took data from 50 different cars as we went through this, and that's our total number. Okay, so when we do a relative frequency distribution, we relate it to the total. Okay, so when we relate it to the total, this is 11 out of 50, which has a relative frequency. If I convert that to a percentage, that is 22%. Now I'm going to show you a really nice easy way to convert to percent, especially if this bottom number is 50. Percentages are out of 100, so if I want to multiply this by 2, that would be 22 over 100, right? Like if I multiply the top and the bottom by 2, 22 out of 100 is 22%, okay? So multiplying by 2 will give me that percentage, okay? The second one, it would be 24 out of 50, which if I multiply by 2 again is 48%, okay? Or you can divide it with using a calculator or whatever, but you're going to get 48%, okay? The next one would be 10 divided by 50, which is the total, and then that would be 20%, okay? Whoop, close, 20%. The next one is 3 out of 50, which is 6%, and then 2 out of 50, which is 4%. Again, I'm multiplying each one of those top numbers by 2 because if I want to convert 50 to 100, I would multiply by 2, okay? So there's kind of how that works. Now we do that so that we can make conclusions like saying 6% of the time I got my food in 225 seconds to 274 seconds. So about, I don't know, however many minutes that is. Yeah, I don't know, like 4 to 5 minutes or whatever, So 6% of the time that happened. 48% of the time I got my food within that range, okay? So we do that so that we can make conclusions, and the percentages, people can relate really well to percentages. So that is a relative frequency because we're relating it to the total. Relative means relate, okay? And then the last one is a cumulative frequency distribution. So cumulative, that's what this column is over here, okay? And you guys might have heard, we've talked about this like at the end of every semester, we take a cumulative math test, okay? Except in stats, you don't do that because we do projects. But all of the math classes you've taken so far from me, you've taken a cumulative test, which means all of the information from the chapters are combined together for that final semester test. It's a cumulative, okay? So this is how this works, okay? In a cumulative test, all you're going to do is add each one of these together as you go down. So in the first step, we have 11, okay? Because there are 11 in that first category, okay? But then for the next one, we add 11 and 24 together, which is 35, right? Okay, and then from there, we continue adding. So I add 10 more, and that's 45. And then from there we add 3 more, which is 48. And then from there we add 2 more, which is 50. And that's like accumulating. It's like adding over time, okay? And so the reason for doing that is so that we can say this. Let me say, like, let's say we're picking on this category. What I can say is, if I were to ask you how many customers had below 224-minute wait time, okay? How many customers were 224 minutes, 224 seconds or below? How many customers had to wait less than 224 seconds for their food? And you can look at this number and say 45, because there are 45 numbers that go on back this way, right? Like 10 plus 24 plus 11 is 45 numbers, right? So that cumulative frequency tells you all of that information, right? Like from there and below, how many people had to wait less than 274? And that would be 48, right? How many people had to wait less than 324? Well, that was all 50 of them had to wait less than 324. So cumulative frequency is like adding or combining them each time, all right? So hopefully that made sense. You're going to have to do that on your homework assignment, and let's, yeah, they don't actually have us do, yeah, that was it for relative and cumulative frequency. Okay. Now the last thing that they talk about is the patterns that we can see a lot of times with these frequency distributions. So I've already talked about like the ages of women and saying that like the younger women are the ones that typically were winning the Academy Awards. Okay. Because women don't age well. And so if we go to like this one right here, critical thinking, using frequency distributions to understand data, we have that here. We're talking about, let's see, frequency distribution showing a normal distribution. The majority of the time, your average right here in the middle is going to happen with the most frequency. So the most times it's going to be like a data value in the middle. If you think about that in terms of height, right? The majority of the people are going to be about average height, and then you're going to have 2 people down over here that are really short people in this category. And then you're going to have 2 people over here that are really in the really tall category here, okay? So, but the majority of the people are going to be about average height, okay? So if you, again, we're talking about time here, but if we were talking about height, that kind of makes a little bit more sense, okay? And what a normal distribution looks like is it looks like a bell curve, okay? And I have posters of this hanging up in my room. We've talked about this before in algebra, but like you have a few people down over here that are on this tail that are the really short people. You have a few people over here that are the really tall people, and then you have the majority of your people here in the middle. That's why this is such a high hump, because we have the majority of the people in there that are about average height, right? Right in the middle, okay? So not very many, and then the average has the most number of people in that category, okay? So, one of the things or one of the trends that we can see with a frequency distribution is whether it has a normal distribution or not, okay? And when it has a normal distribution, the frequencies start low, they build up to a high number, so they went from 2 up to 30, and then they went back down to 2. Now, it doesn't have to be completely symmetric, like maybe it went from 3 to 9 to 30 to 8 to 2, right? That's not completely symmetric, but it's pretty darn close, okay? So just use your best judgment to say like whether or not you think that those are about symmetric on either side of that number that's in the middle. So it says the distribution is approximately symmetric, so it won't be exactly the same numbers on either side like this one was. 2, 8, 38, 2. It won't necessarily be the same, okay? Now, another thing that we have to consider, or a trend, is that if they give me a frequency distribution that looks like this, okay? And we're talking about the last digit of your pulse rate. So like, let's say I took my pulse, and normally I would have you actually take your pulse in class, but maybe we'll do that at some point. And let's say my pulse always runs high. We'll say it's like a 92, because it's usually like super high. I don't know why. Most people's are in the 70s, but mine is usually really high. So 92, let's say, okay? When I got 92, it says the last digit of your pulse rate. So I would be in the 2s category. I would be one of the people that's in here, right? Okay. Now, if I ask you to take your pulse, we have 0 people that are getting 1 for a last digit. So like nobody is getting 71 or 81 or 91 as a pulse, right? Nobody's getting any of those numbers. Nobody's getting a 73, an 83, 93, anything that ends in a 3. Nobody's getting somebody that ends in a 5. Nobody's getting anything that ends in a 7. Nobody's getting anything that ends in a 9, okay? And so we have to think about like why that is. Is that really that 0 people had a pulse of 71 or 0 people had a pulse of 81? Probably not true, but what's happening is that they are taking their pulse, and your pulse goes over 60 seconds, right? You're supposed to take your pulse for a whole 60 seconds. But what they're doing is, a lot of times the doctor's office does this too when they take your pulse. They will only take it for 30 seconds, okay? And then they'll take that number times 2. So if I got 92, that would mean I was getting 46 beats out of 30 seconds, and I was multiplying that number by 2 to get 92, okay? So when I multiply by 2, I'm never going to get any odd numbers, right? So this frequency table can show me how that data was collected. Like I was only collecting that data over 30 seconds and doubling it, okay? I can gather that information just by looking at this frequency table. I can tell you what they did exactly to gather this information, okay? So it says one reasonable explanation is that even though the pulse rates are the number of heartbeats in 1 minute, they were likely counted for 30 seconds, and then the number was doubled to create only even numbers, okay? All right, let's go down to this next one, which is something they talk about that are gaps, okay? So what we have going on here is we have the weights of pennies, right? Like how many grams a penny weighs. And I have 18 pennies that weigh this much and 19 pennies that weigh this much. And then I have a huge gap here. And then I have a bunch more that are weighing like in these 3 categories. So why do I have 0 pennies that weigh in this mid-range, but I have a ton of them here and I have a ton of them here? Like there's a huge gap in that, okay? And so gaps, a lot of times in a frequency table, will tell us a story, okay? Like how the data was gathered, or when the data was gathered, or something changed to the weight of a penny to make it, somehow heavier or lighter over time. So let's read this and we'll see what happens. It says, this suggests that we have 2 different populations. Pennies that were made before 1983, in which case are 95% copper and 5% zinc, and then pennies made after 1983, which are 2.5% copper and 97.5% zinc. So pennies used to be made with a whole lot more copper, hence the reason why a penny looks like that bronzy copper color, whatever. But nowadays they're made with more zinc than copper. So one of those elements is heavier. I'm not quite even sure which one, copper or zinc, but one of this grouping is from pre-1983 and one of them's post-1983. Not really sure which, because I don't know which is heavier, copper or zinc. I have no idea. Look it up, and then you can let me know. But that's telling us that something happened with the pennies over time to change how heavy or light they were, okay? All right, and then the last thing that we can do with a frequency distribution is we can compare 2 sets of frequency tables to come up with some conclusions. So not only did we do McDonald's data, but we also did Dunkin' Donuts data. So we're talking about like drive-through lines and how much time you're waiting in line at McDonald's versus how much time you're waiting in line at Dunkin' Donuts, okay? So 22% of people waited between 25 and 74 seconds to get their whatever items at Dunkin' Donuts, okay? 44%, or the majority, are waiting between 75 and 124, okay? Like a lot of them are waiting that amount of time, okay? Versus all of this data is coming from like the other regions. So like 48%, or the majority, is happening from 125 to 174. So you can just kind of like, even just by looking at this frequency table, you can see that, like these numbers are a lot lower on the scale versus these numbers are a little bit higher on the scale, which means that the majority of the time you're going to wait less at Dunkin' Donuts than you are at McDonald's, right? That's just the way that it works, the way that these numbers are set up. These are lower numbers than these ones are. Typically, you can kind of see how that shift is made. So in general, we can come up with the conclusion from this frequency table that Dunkin' Donuts, you're going to wait less in line. Not always, but the trend is that on average, you're going to wait less in line at Dunkin' Donuts to get whatever breakfast you're getting or whatever meal you're getting versus McDonald's, okay? And just looking at that table, I can see that, okay? So again, frequency tables, we're gathering data, we're putting stuff in there so that we can draw conclusions and make generalizations about our data, okay? That was a lot of stuff. Your homework is a lot. It's a long thing. That's why we're doing it over 2 days. Use your time to work because it takes a little while, okay? And that is all I have for you on Monday. I'll answer any questions that you have.